Hello, everyone. I'm Zikai from the Joint Institute of Zhejiang University and University of Illinois at Urbana-Champaign. So we all know that constraint solving has long been a challenge for symbolic execution engine. KLEE has done a great job to speed up the constraint solving. One of the pieces of KLEE that has helped is the independent solver. At high level, given a query and a set of constraints, independent solver eliminates the constraints that are irrelevant to the queries. So in order to identify those constraints, the first step is to construct the independent element sets of symbolic variables that involve in each of the constraints. The construction requires working through the constraint to collect the relative symbolic variables. The constraint and then KLEE initiate an element closure, starting with the independent element set of the query. And in this example, it contains only one variable, I. And then the constraint whose independent element set intersects the closure, which is the first constraint here in the example, is selected. And the closure is updated as the union with that of the selected constraint. This process is repeated until there's no more constraint to edit, and the remaining constraints are eliminated and not passed to the next level solver. And here we only show very simple constraint. In practice, the constraint can be more complicated, more nested, and involve more variables. Constructing the independent element set requires iterations through those constraints, which, although not much, but do take some time to construct. And this is our motivation to introduce a cache, a hashing map from symbolic expression to the independent element sets. To get the independent element set for a constraint, the updated independent solver will first look up the cache. If an entry is founded, then the existing set is used. Otherwise, the set is constructed. In this way, we only build one independent element set for each constraint. And since the actual set is stored in the cache, we can now store only pointers in the work list of the selected constraint. It also reduces the overhead of copying in the codes that follows. And initially, we introduced the cache for our extended KLEE, which is used to provide automatic feedback to students on their LC3 assembly programs. LC3 is an educational assembly used in the introductory programming courses at UIUC. So we make use of KLEE's infrastructure for symbolic representation and constraint solving. But we construct all the high-level modules, including a symbolic executor for LC3 language. We call the extended KLEE as KLC3. And for the details of KLC3 and the other tools we implement, please see the talk given by Tinkai Liu tomorrow at 1 p.m. So the independent element set cache boosts the performance of KLC3. For one of the most complex, most time-consuming LC3 assignments, for which the student are required to write an depth-first search to fill their weekly schedule with a list of actual events. So we test the effect of the independent element set cache on 960 student code samples. It turns out that the student program will have constructed a large number of independent element sets without the cache. And with the cache, the hit rate is generally high. And as we use KLC3 to provide automatic feedback, we want the feedback to be in time. Our goal is to provide the feedback within 5 minutes for any submission. So without the cache, the 5-minute timeout rate will be over 65%, while this number is reduced to only 30% with the cache. And for the samples that didn't time out, the fraction of the time spent in KLC3 with the cache to the baseline is shown in the image on the right. And the orange line shows the accumulated ratio of the samples that belows a given fraction. The original KLEE also used the independent solver, so it's natural to infer that this optimization can also benefit the testing of C programs. So we collect some student code samples for another C assignment from the same introductory programming courses, which similarly involve depth search. We compile those samples with CLang 02 and test them with KLEE. And for all the settings, we enable the array transformation described in this 2017 papers, as they are shown to be effective for those programs. It turns out that the speed up for the cache is less impressive for KLEE. The average speed up is only 1.07 times. So we got hundreds of samples for both KLC3 and KLEE. One of them get significant speed up, while the others not. What are the reasons? One of our explanation is that KLC3 programs typically involve more instruction than the C programs compiled to LLVM IR. So the LC3 is a simpler ISA. For example, there's no multiplication instruction in LC3, and multiplications are typically done with loop of addition, which introduce more queries to the solvers. And therefore, the overhead of constructing the independent element sets is larger. And also, for simplicity, when we implement KLC3, we let the execution states focus on symbolic memory reference and make those address concrete values in each of the resulting states. For example, a symbolic index into an array can be 0, 1, or 2. Then the state will focus into 3, each with one of the concrete values. The forking introduced more states and more instruction, but the queries are simpler, as there's no symbolic access into array. We implement the bounded forking as an option back into KLEE and rerun those samples of the student code of the C assignment. It turns out that the number of instructions increased by 2 to 4 times, as shown in the top image. However, the actual time spent in KLEE reduced by more than 2.5 times on average. We found that as the instruction increased, the number of queries that issue to the solver front end is also increased to around 10 times, as shown in figure A. However, the complexity of each query is decreased. The figure B shows the average number of symbolic expression involved in each query. And the queries that ultimately reach the STP solver backend is about the same number, locating around 1 in figure C. And since the query is simpler, the time spent in the STP solver is much less, which gives us a total speed up of 2.5 times. We also find that the forking is complementary to the independent element set cache. So the more queries means more set is required. However, those new queries are associated with constraints that are highly overlapped, as they come from the same execution state before the forks, and therefore the cache is better leveraged. The combination of the forking and the cache give us the total speed up of 6.5 times. And in summary, we think the independent element set cache is effective for a specific type of programs. For the 2 assignments we have tested, their control paths are highly dependent on the input data. Both of them use the depth search. So even without the forking on symbolic address, there are still a reasonably large number of execution states. And with the forking, the number of states increase but not explode. So it gives us an overall gain in the timing. Also, both assignments involve a lot of array access, which we think is costly to be handled by the solver, especially the one with the symbolic index, as mentioned in the previous two talks. And last but not least, those two assignments spend reasonable fraction of time in the solver rather than spending all the time executing the instruction. In fact, we have tested a few core utils with the forking on symbolic address. It turns out that those programs spend most of the time in the standard library, so making the optimization less effective. And in conclusion, we think that the independent element set cache is effective for this kind of programs. And that's all for my presentation. Thank you. And if you have any question, I can take them now.